Quantum Foam. Episode 16. Newton's Gravity.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
this is going to have to be a different test of the broadcasting system. This is going to have to be a test of the emergency broadcast system. This is a test of the American Broadcast Association of your ass. It's noon today. It's a great Saturday afternoon. The weather is nice, approaching 60, a little breeze. Random people are chatting away in their own lives in the courtyard. You can hear them talking into electronic devices to other people who are talking into a receiving electronic device. People still hold them up to their faces. They don't like to talk to the air or appear like they are talking to the air from afar. Your guess is as good as mine as to the reason as to why that is, and so we move into our subject.
You seriously actually have a courtyard there? It seems that the world may not be completely lost after all.
And sort of as a precursor to give a little background as to why in the hell I think I'm qualified to be telling all you people this. There are certain things as synchronicity, coincidences, fate, random events in our reality which tend to make us think we are being guided in a certain direction. Put it however you want, but I remember in 9th grade we were going over Newton's third law of motion. It was section 3, chapter 3, page 33. We were doing this class at 9:30. We looked at the clock and it was 9:33. There were more of these.
The date had all threes in it as well.
But even the teacher...
I've heard of such things. How do you know one of the other kids didn't feel that way more so than you? I mean, I guess none of them went to college for physics, however, like you did.
The teacher pointed it out, and he marveled at how weird and what a coincidence it seemed that we were doing all this stuff, and the room number was 33. It was on the 3rd floor. I don't even remember how many coincidences there were.
I'm sure there were a lot.
But everything dealing with 3 and Newton's third law of motion. But I pointed this out, I think, to him, and that's how I was involved.
Mighty slim involvement. Let me run some calculations.
And so hence with 4th, I've always liked physics. Since 8th grade, I liked astronomy. I found out I liked it. And so I found out that that's actually studying physics with a flavor of astronomy, which is a very, very large part of physics. Maybe half of it. Who knows? You could split it in half and say physics of other stuff and physics of stars. So that covers astrophysics and orbital mechanics, which you proved mathematically.
Damned right. That shit took a life's work. Let me tell you, I wouldn't be here if I didn't do that. You wouldn't be here. All the shit you guys use these days to view your stupid ass content is all because of me. Motherfuckers.
And Kepler had shown it empirically. So, 1 and 1 is 1 and the same.
Motherfuckers.
We move further into this gravity stuff. What exactly is it? And how can we understand it? And how can we apply this towards the theory of everything in which it has a major part? Right now, we know that there is a major loophole in our current understanding of physics because we cannot understand gravity to the point of manipulating it in the way we can do with chemistry. We understand chemistry 100%. That's why I don't believe that fucking bullshit you're talking about with this alchemy horse shit.
Damn it. I told you not to bring that shit up. What the fuck, son of a bitch.
You guys didn't understand chemistry. We do. It's just a fucking thing you put in one thing and another thing turns another color, and then that it is. That's all it is.
Whatever. You're just lucky. That's all I'm gonna say.
Now, the fundamental chemistry is a different story. Are you really talking about chemistry or just physics? And so that's when chemistry becomes physics, when it goes up to the scales of molecules of things like water and other larger chemicals to common things like a tree or something, a plant, the size of those cells. Now, unless you want to get into photosynthesis and then compare it to baryogenesis, we better stay on task with this one. So let's check out the gravity of the situation. There is different things that people discuss that help you remember this stuff, but it has to do with Newton, U, Apple, moon, inverse square law, etc. Gravity, value of G, big G, little g, down, up, stuff like that. U, Apple, moon, inverse square law, It deals with all of that. And so we know that the net force is equal to the mass times the acceleration of an item. F equals ma. We're all aware of this.
That's my second law.
And so the universal gravitation equation is simple. The force due to gravity, or how gravity interacts. We've discussed this. m1 times m2 over d squared, or r squared. The radius, or the distance, or whatever, that scalar value squared. So it's proportional, meaning equal. You're doing math equations in both directions, depending on what you're doing. And we know that the distance of two objects is being modeled as point particles. So when we involve other things, we involve other things. To go into these laws of gravity, we sort of need a little bit of a primer on Kepler as well. I didn't feel that we needed to go deep into his stuff yet. There's plenty of time to do that later. However, for now, let's briefly go over his three laws. They deal with circular motion, principles of satellites, the math of satellite motion, weightlessness, energy relationships in orbit, things like that. And so in the 1600s, Kepler proposed three laws of planetary motion. Essentially, these weren't exactly correct. However, they did describe generally the way that planets do move.
This is pretty much the reason why I built my math. I saw something in that stuff he was talking about. I knew there was more to it. This equilibrium stuff. There had to be a ground math that fit into such a system. And I built it up, motherfuckers.
And so, even though he wasn't exactly right on his math, he was pretty damn close in figuring out what really does happen.
Precisely.
And you were able to actually put out the math to describe this, and that's one of the main reasons why you invented your math, which is a pretty good reason why we are discussing this here. However, what he did, what Johannes Kepler did, was summarize the carefully collected data of Tycho Brahe, whatever. That was his mentor. And he wrote these three statements, which were basically his laws for the planets for a sun-centered solar system. So, we say, Kepler's effort that he put into this is what we are congratulating. The theory was right. The math was inaccurate.
They were accurate for just orbits, though.
As with many scenarios in the history of natural philosophy, as you would say.
Physics sounds cool. There are no complaints from me.
So these three laws can be described like this. Law 1. Path of planets about a sun is an ellipse. The sun is at a focus. Law of ellipses. Piece of cake. Second law. An imaginary line drawn to the center of the sun to the center of a planet will sweep out equal areas in equal intervals of time. This is the law of equal areas. And this just allows us to do areas, and you figured out a way to infinitely deal with the problems under curves.
Yeah, there are still problems with the Riemannian sums conjecture. How much is enough to say you have a sufficient sample of infinity? Some of these questions surely will never get answered.
However, as we have both figured out, there are problems with this in dealing with relativistic gravitational metric tensors describing field equations that are based on a mix between an amalgamation of quantum mechanics, Dirac equation mathematics, and Einstein mathematics. So right now, that's the best we have. We need to find something better. We are investigating all of this stuff to try to do that. The most important, in my opinion, is the third law of planetary motion, and this is the ratio of squares of the periods of any two planets is actually equal to the ratio of the cubes of those planets' average distances from the sun. You get a harmony out of this. You can get three variables that spin around like a song at a tempo. So we are able to triangulate because of this.
Gotta hand it to you. Those are some of the same insights I had when I came up with this shit.
Trigonometry describes algebra. Trigonometry describes calculus. Calculus describes trigonometry and deals with infinitesimal issues. And then what does linear calculus do? It puts in a computer algebra system a data structure of complete equations similar to the Dirac equations. You know, Schrodinger's equation summarized, reformulated 4 times, and diagrams getting built and used by Feynman, put in a diagram. That's the best we essentially have now for this. But we are able to properly look at this entire subject and find a way to triangulate future math requirements for purposes of financial outlook and statistics, planning, and various other things that are required to keep the infrastructure of society strong. So we need to be able to do things like combat all types of warfare, from digital to medical to physical to nuclear to dimensional to any kind of warfare, because we don't want to be bothered by some warring nation or some warring party party or some warring species that want their planet back.
Dimensional warfare.
We're sorry you left 500 million.
Dimensional warfare.
We don't care, man. We're here now. Fucking go away. Go find another hot world where you can be a fucking reptile and do weird-ass reptilian shit. We don't do that here, man. We're apes, so we do shit that apes do. We don't fucking do that other shit. Eat everybody and fuck everything. Fucking weird shit, man. Go to another universe or something. Leave our math, leave our physics alone. So we assume that our physics is the same as at the beginning of the universe. It might not be.
It is, according to special relativity.
But we cannot operate any other way because I can't just make up some new laws of physics that I say all of a sudden happened at this time, this many billion years ago. 13.7, and then they changed it, 13.6 actually, or
13.8.
whatever, man, 14 billion, none of it's right. We're going to be like,
What? It's actually 29 billion years old? What the fuck? We couldn't see it until we put the new eye up.
Maybe.
who knows? We think that might happen, but I don't think that will happen. Something else that's weird will happen. And your guess is as good as mine on that. However, if my guess is all right, then I'm the one who gets the credit for coming up with this theory. So, suck it. I'm not doing this for you. I'm doing it because it needs to be done, motherfuckers. Alright, so these three laws that we got out of this, Kepler's laws, it basically describes circles and ellipses and orbits in general. We understand foci math. It's very easy. Because it needs to be done, motherfuckers. It's 1 equals blah blah blah. X because it needs to be done, motherfuckers. It's like x squared minus that, and then when you put it into a y thing, it busts out a circle.
Don't get lazy on us. The equation for a standard ellipse is x squared over a squared plus y squared over b squared, all equal to 1.
And one of the foci are imaginary, the other foci is the sun. So figure it out. It's two parabolas going into each other. So it's pretty easy to do inverse parabola math in the form of a circle that's elongated into an ellipse. And that's what we did with calculus. So this stuff was done by these guys back then.
Damned right. I put my heart, mind, and soul into the presentation of the most advanced mathematics that had been known by man to date.
So it's to give a short description of some of the things that this affects and how this was extended by you to planetary motion. We understand planetary motion now. It was described by Kepler back then, and now it was being described by you with the new calculus you came up with. Calculus, and you essentially plug in your equation. And to give a few small examples of distances and how we would apply the law of harmonies to these orbits, the Earth is about 1.4957 times 10 to the 11th meters from the center, and Mars is 2.278 times 10 to the 11 meters. So that's obviously further, the fourth planet. Keep in mind that this t squared over r cubed thing, the t squared over r cubed ratio is actually the same for Earth as it is for Mars, because they're both in the same damn orbit. It's basically nearly the same for all the planets, and amazingly, every planet has this same t squared over r cubed ratio. Why is this? Because it's these laws, and so obviously in real life, it's not perfect because it moves, so we don't know where it's at in the wobble. We're trying to calculate all these wobbles, man. We have this program, there's another program that we use to model these. I can't remember if this one includes relativistic mechanics or not, but I know one of these programs can model Newtonian mechanics basically 100%, because we can see it on the screen. So it's the same thing that we see in real life, and it's also the same thing that our simulations project. So I think we understand this stuff. We're talking different AUs. It's easier to look at things in this regard. Mercury's 0.39 AUs, astronomical unit, 93 million miles or so.
The average distance from the Earth's orbit to the center of the Sun.
Earth is obviously 1 AU. These are average distances. Mars is 1.52 AU. Jupiter is 5.2 AU. Saturn is 9.54 AU. Uranus is 19.18 AU. Neptune is 30.06 AU. And just for shits and giggles, Pluto is 39.44 AUs away. And the funny thing is, all of these in terms of years squared over distance of AU cubed, they all equal about 1. Pluto is 1. Neptune is 1. Uranus is 1. Saturn is 1. Jupiter is 0.99. Mars is 1.01. Earth is 1. Venus is 1.01. And Mercury is 0.98. The funny thing is, if you look at those averages, why are the planets and planetoids out towards the rim? Why are they exactly 1? The last 4 are out of these 9. And so Jupiter is a little off. Then Mars is a little off.
Go back into the material.
For accuracy's sake, it takes about 3.156 times 10 to the 7th seconds for our Earth here to orbit our sun 1 exact time. 1 revolution of our Earth around the sun. That's what? 3.156 times 10 to the 7th? What? Seconds? What?
come on.
Okay, but these laws provide an accurate description of these orbital mechanics, and Newton used these to describe these orbits with a calculus that was provable. And so we understand this stuff pretty damn well at this point. Law of gravity, it's pretty fucking simple, man. F equals G, m1, m2 over r squared. Just figure it out. I think they get it. I wouldn't exactly say it's quite that simple, but it took a lot more than you might think to figure out that inverse square distance law thing.
Finally. Break time. So much material, I swear.
All right, we are about halfway through
Episode 16, Newton's Gravity.
of quantum foam. Quantum foam.
So just keep that in mind. You motherfuckers aren't allowed to know this. But I digress. I suppose we can get a little bit more done here. So this deals with what exactly is this gravitational constant. There had been earlier attempts to figure out what this gravitational constant was by recording oscillations in a pendulum. There was a problem with this time. Nobody could decide what was the proper inertial frame of reference to go off of because anybody can come up with anything. And we did not realize until Einstein that relativistic equations could describe one thing and another only in that they were relative to one another. So the fact that relativity is a thing was the revelation. It had something to do with that problem you were having with Robert Hooke as to the originality of this inverse squared distance law. And it's like, that seems like such a simple thing, yet people could have said this, but obviously they didn't know. They were still stranger to the idea, as you put it.
Those idiots were stranger to the idea. Yes, everyone has a nemesis, a rival that is on the other side of the courtyard or the city or the country, and someone who turns out to be just a big pain in the ass. Trying to say that they published this stuff before me? Bullfucking shit. None of them had any math that made any sense to anyone. Robert Hooke didn't even understand velocity.
They were close. They were theorists, logicians, philosophers, philologists, whatever the fucking word is. These were just other people who were guessing at the math that described celestial motions.
A pretty tough business. Don't kid yourselves.
Planets and such, and gravity. The only person who was even kind of right was you.
I knew I was right from the very beginning.
Isaac Newton. He had the idea to know that even though his math described this such and such, there were still unexplained perturbations that were caused by the center of the solar system. And we don't know what this is, but he knew there was some shit going on that people could not figure out, and he knew he couldn't figure it out. That describes the problem with Mercury being affected by the gravity of the sun. Apparently it was. Well, I'm sure it's been said somewhere, but I've never heard anybody say it. Anyways, a few more things need to be said about Kepler, because Newton had his rivalry, and so...
You can't plagiarize if you have mathematical proof. Just saying. Robert Hooke can suck it.
Kepler, in a matter of speaking, had his as well, but this one was a little bit different. Basically, Tycho Brahe, he spent his whole life taking astronomical surveys of different bodies in the sky, something that can really only be done over a matter of many years. And upon his deathbed, he enlisted a young version of Kepler to take a look at his data sets and to form his own opinions, while secretly keeping his own observations secret. He had his own Earth-centered model of the universe, and he withheld some of the more important observations from Kepler because he didn't want Kepler to use them to prove the Copernican theory correct. And it was correct, however, for the wrong reason. It wasn't quite right. His math was off. Kepler's math was a little off for certain things, but not for the planets. He found an imaginary line that went between the ellipses and was wondering why there's some kind of symmetry for this. What is a circle that's not a perfect circle? Everybody at the time had this symbolic idea. It was like a mystical belief because people didn't quite understand things the way they do now, so they believed in mysticism of this sort still.
I still stand beside my alchemy. I saw some scary shit
coming from the Dark Ages, but many philosophers of this era had a mystical belief that the circle was the universe's perfect shape, and so divine order and the orbits had to be circles. They're not circles, they're ellipses, and the ellipses draw an imaginary line that goes from one axis to another, and he was able to find out that there is a focus, one of them is the sun, and one of them is imaginary, in which the planets orbit.
Technically, the other foci would be inside the volume of the sun.
Even with the data set that he had, Kepler was able to use, to everybody's dismay, that planets are actually orbits of ellipses, and these helped him define his three laws. And remember that the first one is planets move like an ellipse. The second one is the area. So triangles having the same area is a better way to describe it, because you know how there's also a property that the degrees within a triangle always equal 180 degrees. So whether it's a right triangle or any other triangle, they always equal up to 180 degrees. So using those for the surface area. And a lot of this stuff is adapted from Tycho Brahe's work, Introductory Exercises Toward the Restoration of Astronomy. That's translated. And also some stuff from Kepler is actually adapted from Epitome of Copernican Astronomy, and that's translated. So this is the same stuff that Newton had, essentially.
Yeah, but we spoke a lot of French. It was easier for some things in some places you wouldn't understand in this day and age where you are located.
And it still holds true. However, we are moving into what his contributions were, which is why I'm naming this Newton's gravity, because it is gravity, but it's Newtonian gravity.
Been wondering why this is supposed to be my gravity, and you have mostly been talking about Kepler. He was a great astronomer, but I'm the physicist here.
So it is the first mathematically complete version of physics and math that were understood and that were created by him.
I extended the motion of planets to a mathematical framework named calculus, where all motion of any kind is described fully with accompanying mathematical examples, provable solutions.
This stuff still works 100% for stuff like cars and trains and balls and ping pong balls and pool balls and basketballs and all that stuff. That is why we are going over this now, because it needs to be done before we get further into more complicated areas of study. The main thing that Kepler did was define orbits that were ellipses, and then we move into what Newton had done. He actually used Halley's Comet that came in 1680, or Halley's Comet 1681, maybe 1682.
It went by the Earth twice, one each year. I hadn't even finished my math yet. Was a crazy time, just like now for you, when you know the math but everyone else is so stupid that they can't understand it until you publish it in layman's terms. This podcast is an attempt to do exactly that.
Back then, Halley's Comet only comes about every 75 years, so it came in 86, before I was born, way before, not too far before, and it won't come back again until 2061, so we got 41 years for this. Maybe after all this time, I'll prove that comets' trajectories are parabolas, just to see if...
You gotta test that FTL math of yours as well.
Do what Newton did, because it would be fun.
It was fun.
Also, in 24, I wasn't able to in 17, but in 24, I'm going to try to recreate the photo plates that would help us prove relativity as well, because there may be another experiment I'm going to design that can prove some other stuff, and it's only going to be used during an eclipse due to radiation and other things. They need to get that telescope up there, and everything needs to be ready to go, although this time they will have a further frequency, a higher frequency, because they will be looking in the infrared, which will allow them to bend it a little bit further and mathematically bend it to where they can possibly see a little bit further back, and we can see what the exact story is right after the first 3 minutes of this supposed Big Bang. And we are most interested in now, and also the loop quantum gravity people are most interested in seeing if we can see any information that comes back out, or any information that came from another universe, so to speak. And so if it does, then it can, and it proves some things that we will get into at a later date. However, for now, I was just describing the relationship between Tycho Brahe and Kepler, which were sort of the legends of natural philosophy of the day when Newton was part of the Royal Society, and we'll get into that now too.
We should still try to limit the amounts of information that we throw at these guys per episode, because this shit gets confusing, even for us. Just keep in mind that in my day, your position was closer to your degree than you guys treat your jobs, your work, your schools, your public, and your so-called private sector business. Research and development, as you know it, has come a long way, and that part of it I am glad to see such success.
Right, so this Royal Society was actually somewhat of a structured structure that is similar to our colleges and academics and professional societies of science that we have today. We have Science Magazine, Nature Magazine, National Geographic, pictures of wildlife. Sandhills Publishing, publishing pictures, digitization of photographs and art involving wildlife of the Great Plains of the Midwestern United States.
It was different back in the day.
You know, these guys were the guys who were older than Newton. They were coming up with systems of the world in the 1660s, when Newton was not of the age to be producing such profound changes in the way that everybody thinks of science. You know, there were other people that you talked to, that you were speaking to. You guys did it with letters back then. Who's that Boljo guy?
He was another astronomer. It was also Mr. Edmund Halley. He got the comet named after him.
That French astronomer, mathematician. You guys also studied theology. He was an active member of the Republic of Letters, that stash of all those letters and stuff that you guys...
That's a stupid name to call that, but whatever.
That's how they did it back then. So, who wasn't a philosopher of the day? Everybody had their opinions, and people respected them because they were recognized as coming from somebody who knew what the fuck they were talking about. There were other people that discussed this and had ideas about the inverse laws. And even Hooke himself, he has no room to talk. It was down on paper that he had guessed something wrong about the velocity, so that's something so common. If you knew what the fuck you were talking about, you wouldn't say the velocity does this.
Tell me about it. He was a smart man, but not as smart as me.
You wrote your laws about it, and then you backed it up with math. And that's how you do it.
And so, it doesn't matter these days. These are just
Details that don't matter. What matters is the universal law of gravitation. It doesn't matter. It still works for orbital mechanics at a Newtonian level and at a level that completely encompasses our daily lives and the size of an average human, which is about 2 meters, 6 feet. But I do understand the physics of this stuff. So I am now describing it to you, and that's who the fuck I am. I am describing it to you, and you people, and all you other motherfuckers. So if we're talking about me, or we're talking about you, or we're talking about your book Principia, talking about Hooke, what are we talking about here? Those are menial details that do not matter. So what does matter is that it was actively debated in the court of science during this time, and we generally can attribute this to being pretty organically true of how this stuff about gravity was figured out during this time, whether they understood it or not.
I get it. This is setting the proverbial stage for when I discovered my gravity. This is the same stage now where you are discovering a method to communicate at faster than light speed. This uses actual quantum-derived artificial intelligence. Pretty neat.
There were other people who acknowledged you, other reputable people who acknowledged your accomplishments and your math.
To some, recognition is a must.
They knew there was something profound about it. And even to this day, we know this. To this day, we have experimental plots showing values for big G, which is gravity. We can look at gravitational field strengths and the distance from inside the Earth and the location as it applies to a certain location on Earth. This helps us describe bodies with spatial extent. A ball, a planet, something with a three-dimensional complicated structure that needs to be dealt with individually and then dealt with as a point particle. We generally just use gravity near the center of the Earth, but obviously there are some applications that require a finer degree of precision and accuracy. So if you're just describing a gravitational field, use it as a vector field. You can use Gauss's law. That motherfucker was so smart. Vector field, vector field, vector field, vector field. But it's Gauss's law for gravity. Or it's a flux theorem, I guess. Whatever. Vector field, vector field, vector field, vector field. That sounds stupid. Or cool. But it's essentially equivalent to Newton's law of universal gravitation. So, Carl Friedrich Gauss, although Gauss's law for gravity is equivalent to Newton's, there are many situations where Gauss's law for gravity can offer more convenience or a simpler way to do a calculation. But
whatever, I would always use my math.
What are we doing here? We need Newton's laws for this stuff. You can use Gauss's law for certain things with electrostatics and Maxwell's equations. So those partial differential equations and the Lorentz force law can form a foundation of electromagnetism, how you understand it. But classical optics and electric circuits are definitely understood by us. So
after I built the first reflecting telescope,
we've had these mathematical models for some time and have been able to build technology with them for some time as well. Obviously, there are problematic aspects of this expression of gravity. So at a later date, we will attempt to describe gravity on a basis of a new model for the description of the theoretical particle, a graviton.
We were always more interested with the waveforms. This graviton is one of the last things that need to be addressed with that damned standard model of particle physics.
We're going to examine whether or not there is a graviton particle, or if it is just essentially always going to be an imaginary mathematical quantity that we carry along with the interaction with another fundamental particle. So we may know more about this at a later time.
We need observations.
For now, this is all we will describe regarding gravity and how we are going to be using the description of gravity from here until a later date when we have a more fundamental description of gravity.
My gravity still holds up. For now, that's what I get from this.
And that is it for episode 16 of Quantum Foam.
Quantum
Foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.